Welcome students. In this lecture we will see that how DFS is used to classify the type of edges in a graph. Now what those edges are, we'll come to it, but before that we'll see two different times, the discover time and finish time. What are they and how they are used basically with respect to depth first search or DFS, right? So now as we can see, one of the important application of depth first search is used to classify the type of edges in a graph, right? So now the nomenclature which I have taken, the discover time and the finish time. The discover time is represented by D and the finish time is represented by F. So this nomenclature has been taken from the Coleman, or the book you call is that Introduction to Algorithms. By many colloquial name of that book is also called as CLRS. I mean, these initials are the name of the four authors who have written this book. So one more important point is that this book, the Coleman or the Introduction to Algorithms by Coleman, is a very good book, and definitely if you see these lectures will come very handy in understanding the book. The book is beautiful, but it's verbose and very mathematical in nature. So if you go through these lectures, definitely it will be very easy to understand the concept described in the book. So coming back to our lecture. Now what does this discover time and the finish time means? So for example, if we have a vertex or a node U, so how will we write, mention the discover and finish time? On the graph we use this notation, D/F. D means the discover time of this vertex or node and F is the finish time. Now what these means, I'll come to it. And in the data structure, U dot D is represented by, so whatever the discover time is, that is stored in this way, right? U dot D. U dot D means the discover time of vertex or node U, and U dot F means the finish time of the vertex U, right, or node U. Now what these times are? So as we have seen, now we are very familiar with how DFS works. So I'll take an example in making you understand what this discover and finish time is. So by definition, discover time is the time the node or the vertex is discovered for the very first time, right? And the finish time is when you are done exploring all the edges or all the vertex which are adjacent to that node. Once you are done and you are coming back, that particular time is called finish time. So don't worry, I'll take an example to make you understand it more in a more better way, right? So for example, let's say, and I'm assuming that you are quite familiar with how DFS works, right? So I'm not going to spend much time over it. So let's start tracing these finish and discover time on this graph. So for example, if I start my DFS on this graph, and this is you can see this is a directed graph, right? On this vertex A, so what should I write here, right? So I'll write, because I'm starting from here, so its discover time is 0, correct? Its discover time is 0. And now, what is its finish time? Can I write anything over it? No, because this node is just started, it's not finished. So why it's not finished? Because there are some neighbors which are yet to be explored, right? So the DFS, basically we are running DFS over this graph starting from this vertex. So now, as in case of a DFS algorithm, what will happen? Either we can explore this branch or we can explore this branch. Suppose we went to here. So now, what will be the discovered time of B? Definitely 1. Are you getting it? It's very important. We started with A, it is 0. Then the next node which we could have reached from A is B, and we went there. And at what time we reached there? At what time we discovered B? At time 1, correct? Now, can I say B is finished? No, definitely not, because still in this DFS algorithm we can proceed to this vertex C. So now in which time C is now discovered? I move forward and now in time unit 2 C is discovered. Right? Now from C, now yes, there is a path, there are some vertices which needs to be discovered. So we go there, we went to D and discover time of D is 3. Right? Now from D, now look at here very carefully. From D, can we go somewhere else? No, definitely we cannot. So there is nothing to explore beyond D. So now what we can do? We'll backtrack. And now while we are backtracking, so the finish time will mark it as, yes, you are right, 4. Correct? Because in time unit 4, we have started backtracking and we are here. Right? Now again, the same concept will go here. Now you will backtrack, you come to C. Is there anything yet to be discovered from C? No, because there is only one edge, right? And one adjacent vertex D, and it has already been discovered. So there is nothing to discover anymore. So we will finish on C. So what will be the finish time? 5. Similarly, on B, on the same logic, it will be 6. And now, can I write 7 here? No. Yes, you are right. No. Why? Because there is still neighbors of A which are yet to be discovered. So we will try to explore this branch. And here we have encountered E. At which time? Now at which time we have encountered E? We have encountered, because we have went here 6, and then after 6 we just went to this E at 7. From E again there are 2 branches, G or F. You can take any branch you want. Now suppose I came to F, so it's 8. Now is there anything need to be discovered from F? Yes, there is one node D, but it has already been visited, right? So it has already been explored. So there is nothing to explore. So what we get now? What we have to do? We have to backtrack. So I am backtracking at unit at time 9, and I marked it as a finish time of node F. Now for E, now see, come to E and now tell me, can I mark it 10 here? No, just the same logic as we have seen at A, the same logic will apply to E, because there is one more node still yet to be discovered, and that is G. So I'll proceed to G. And now, what will be the discover time of G? So at 9 I'm here, so at 10 I'll discover G. Now what after discovering G? Are there any neighbors of G? No, there is nothing to be explored, so I'll backtrack. The finish time of G will be updated as 11. Now from G I'll backtrack to E. Is there anything else from E which needs to be explored? No. So I'll write here 12. And now finally, which one is left? A is left. And with this, now the whole complete graph is discovered. So I'll finish my algorithm on DFS algorithm on A and mark the finish time on A as 30. Fine. So I hope now the concept of discover time and finish time is clear to you. Let me recap in very fast. Let me recap it. So what you have seen. So you will mark the discover time on a node on the very first time when you have approached that node, right? So you will mark that time as a discover time, right? And finish time when you are backtracking and there is nothing left from a node to be discovered, you will mark it as finish time. And it makes also sense. Why? Because DFS now after that node is finished, right? There is nothing to be explored. So it's finished. That's why we have written it as a finish time. And in case of a discover, it's the first time you are discovering that node, right? Common sense. So it is a discover time, right? Now we'll move on to our next section, that is with this concept in our hand, how to classify the type of edges in a graph, or what are the basically type of edges a particular graph has, right? So let's begin that. So now let's see that what are the type of edges a graph has. Okay, so there are basically 4 kinds of edges, right? So let's start them one by one. So number 1 is tree edge. So tree edge, what does tree edge means? So if there is an edge u comma v, so now I'm assuming that you are familiar with the concept of how edge is represented, right? So for example, if if there is edge A to B, how it will be represented? A comma B, correct? It won't be represented as this, right? No. Why? Because this edge is from A to B. And secondly, in this lecture, whenever I say graph, it is always by default a directed graph, right? Not an undirected graph. So in case of a directed graph, these two edges are totally different edges, right? So we are considering a directed graph. So U comma V is an edge in a directed graph. And what is a tree edge? That if V is discovered by exploring edge U comma V. Right. So what does it mean? So let's take an example. It will be more clear. So U is being discovered means U is being visited for the first time by exploring the edge U comma V. Right. So for example, in this case, let me rub this off. So for example, in this case, from A to B, the vertex V, definitely it got discovered when you traverse through this edge U comma V. In this case, U comma V is A comma B, and then only V got discovered, right? So this edge becomes nothing but your tree edge, right? So let me mark it with a separate color, green, to identify a tree edge, right? And one simple observation can also be that the normal edge in the DFS, right? The normal edge through which you go, you jump from one node to another in a normal DFS is a tree edge basically, right? So A to B is tree edge. Now will B to C is a tree edge? Yes, definitely it's a tree edge, right? Because you are approaching C, you are discovering C for the first time by exploring this edge, right? So this is a tree edge. Now again from C to D, yes, again it's again a tree edge. So tree edge is basically one of the simplest edges to identify. It's the normal edge in case of a DFS. The normal edge which you take to explore subsequent neighbors from a particular node is basically a tree edge, right? So these are all tree edges. Now what will happen? So in this case we have seen, now we have backtracked. Now from A we explored E. So again this AE is also a tree edge, right? So nothing fancy about it, very simple. Now tell me what will be E to G. Again E to G will also be a tree edge, right? So let me also make it as a tree edge, right? Now E to F. So now E to F will be which edge? Again tree edge. And F to D. Now here I want your attention. Now see, can it be a tree edge? No, in this case this edge will not be tree edge. Why? Because in this edge F comma D, right? So you have to be very careful here. See, in F comma D, when you went through this edge, D is already discovered, right? D is already discovered here. So definitely it didn't got discovered by exploring this edge. So this edge is not a tree edge. Correct? Now, had we gone through this branch first, this would have been tree edge, right? So AE, EF, FD, then it would have been tree edge. Now this will be different kind of edge. What edge? I'll tell you later. I mean, definitely in this lecture only, it will be your fourth kind of edge basically. So I think now you are clear with the tree edge, right? Now let's come to back edge. Now this edge is very important because many questions form on this concept, on the concept of back edge. How? Because back edge in a graph implies a very important thing. And what that thing is, let's see, right? So I need your attention here. It's a very important thing. Most of the time if you find any question on edges, I'm pretty sure this will be the question which will be asked, right? In normal competitive exams, semester exams, in interview questions. So for example, if I make a new edge, right? And this edge is from C to A. Correct? This edge is from C to A. Now let's see what is the definition of back edge. Back edge says that if U comma V is an edge, it's a back edge if this edge connects U to ancestor V. Now here we again see a new term, and this term is called ancestor. So what does ancestor means in with respect to graphs or with respect to trees? So ancestor, if you see in the daily life, what does ancestor means? So your father is your ancestor, right? Because you descended from your father. Your grandfather is also your ancestor, right? Because from grandfather to your father and then from father to you, right? Now many people might think that your uncle is also an ancestor, right? But in this terminology, in case of graphs and trees, he is not. Why? Because after your grandfather, it got that branch got separated. If you draw the family tree, if you are aware of the concept of family tree, so your uncle is not part of the is a part of that branch, right? So it's a different branch basically, right? Which is parallel to your father, right? So basically, he is not your ancestor. Now again, your great grandfather, great 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 grandfather, again they are all your ancestors, but brother of your grandfather or the brother of your great grandfather, right? He is not your ancestor, correct? So in that sense, so if we see here, so in this respect, what an ancestor means. So B can be descendant, B is basically descendant of A, C is descendant of B, D is descendant of C. So basically C is ancestor of D, right? B is ancestor of C, B is also ancestor of D, A is ancestor of B, C and D, correct? So now what does back edge mean? So if any edge, so for example in this case, if we have taken the edge, so what is the edge we have taken? C comma D, right? So this is our edge because it is from C to I'm sorry, C comma A. I'm very sorry. C comma A. C comma as A is my edge because the edge is directed from C to A. Now it says that if edge connects U to ancestor V, then it's a back edge. So yes, so is A is an ancestor of C? Yes, it is, and this edge is connected a descendant to its ancestor. So yes, this is your back edge. So this is nothing but your back edge, correct? And I'm drawing it with black, or let me draw it with some other color, maybe not to confuse with this one, right? So let me delete it and let me change the color to red. So this is your back edge, correct? And now we see the other two type of edges, what they are and how to identify them in this graph, right? So now let's discuss the remaining two type of edges. So what they are basically, now there are two types of edges, forward edge and cross edge. So usually many students are get confused between these two edges, and it's really confusing. So you need to be clear with the concept of your ancestor and descendant. So for example, let me again make sure that you are quite clear with it. So let me make simple tree. This is a node. This, now let me ask you, and let me say I gave this node 1, 2, 3 and 4. So is 3 descendant of 4, or vice versa? Like is 4 ancestor of 3? No, it is not. Why? Because as I told you, so because it's a separate branch from here, it has separated from here, right? So what will be the, who all will be the ancestor of 3? 2 and 1. Definitely not 4, right? I hope it's clear, right? And 3 is also definitely not going to be a descendant of 4. It's going to be descendant of 2. It's going to be descendant of 1, right? So now I think now we should begin this again. So what does forward edge mean? That is any edge connecting vertex U to descendant V, right? So this in this edge, this will be an ancestor and this will be your descendant, right? So for example, I just modified the previous graph to include more edges on it. So for example, in this case, this is an edge A to C, fine. So this is an edge A to C. And now you can see, definitely we discussed earlier, A is ancestors to C, right? Because it's a single line of descent, right? And or C is the descendant of A, right? See, so this satisfies this condition. So it means that this edge is a forward edge, right? So you could also see one very important thing here, and let me draw it with some different color. You could see here that is it not just the reverse of a back edge, right? So what was your back edge basically? So back edge was an edge which was connecting your descendant to your ancestor, right? And in this case, what it is doing? This is doing just the reverse. It is connecting your ancestor to your descendant, right? So if I just reverse it, had I made this from C to A, it would have been a back edge, right? So this is the concept of your forward edge. So now, so for example, in this case, which will be a forward edge? So had it been from this edge to this edge, this would have been forward edge, right? But this edge will not be forward edge, right? This edge will not be a forward edge. Now, let's see the cross edge. So now all the three edges are gone. So what's remaining is basically your cross edge. So let's also see that how does cross edge looks like, right? So for example, if we see this edge only, what you can see? See, this is not a tree edge, right? So this is our DFS. So we went from here to here, right? From here to here, from here to here, then we backtrack from here to here, and then this edge is also there, but here 3 is already discovered. So this is not going to be a tree edge. The same case we found it here from F to D, right? Because when we went from F to D, D was already discovered. So clearly this is not a tree edge. Now, is this a back edge? Or is this a forward edge? No, because there is no relationship of ancestor and descendant in this case of in between 4 and 3. So what it is? Definitely this is a forward edge. So in this case also we can see from F to D, this is not a tree edge. Again, there is no relationship between F and D with respect to ancestor or a descendant. So this will be our what? This will be our forward edge. Right? So this will be our this will be our, I'm so sorry, this will be our cross edge, right? I might have said forward edge, but this will be our cross edge, right? And same is in the case of G to F. So now what happened? If you could remember, from E we went to G, so this is a tree edge. Then we backtracked, right? And now suppose this would not have been the case. I'm sorry. For example, from E, if you have went to F, right? If you have went to F, this would have been your tree edge. Then there would have been nothing from F to go anywhere, because all this neighbor is discovered, and this neighbor there is no path from it. We would have gone back. We have gone back to G. Then this would have been termed as your tree edge. And now from G to F, since F is already discovered, this is not your tree edge. Now again, F and G, if you see, for both of them, E is the parent, right? So both of them are brothers, so they cannot be ancestor or descendant. So what this edge then can be? This can be only your forward edge, right? So if you are confused, just go through the lecture again, and I'm pretty sure that you'll get the concept of cross edge and forward edge. So one thing should be kept in mind, that in forward edge, there will be a relationship of ancestor and descendant, and the edge will be from ancestor to descendant. That's why it is termed as forward, right? And the same concept, when it is reverse, it is called as backward, and that is backward edge, right? Back edge. And the cross edge, which satisfy none of these, neither is a tree edge, neither is a back edge, nor is a forward edge. It's a cross edge, right? So with this, the concept of edges are finished. Now there is one very easy question which has asked in K. So it's not exactly related to edges, but I think, yeah, it is the most appropriate time to discuss that question here. So we'll discuss that question.